All right, so as you can see, I've already set up the PE diagram for the next example here. We're going to look at the effects of something called an inhibitor. Inhibitors do, well, in effect, it does the opposite of what a catalyst would do. So instead of speeding up a reaction, it slows it down. However, it works a little bit differently from what a catalyst would do. Okay, so you can pause the video right now so that you can sketch out this PE diagram. It looks very similar to the other one that I showed you from before. Okay, it's just that this time we don't need to worry about the actual values. And you'll notice that I've gone with a generic reaction. A plus B gives you C. So again, pause it right now, jot it down, and then we'll carry on. All right, so you've drawn out the diagram. Okay, still exothermic. This time though, I'll show you what the inhibitor does first, and I'll explain how it does it. So we'll just switch colors here. Let's use this lighter color. Again, because you are starting with A plus B gives you C, okay, you have an inhibitor that we're going to add in, okay, along with your reactants. So here are your reactants' potential energy, and here's the product's potential energy. If you add an inhibitor, it starts off again at the same plateau, okay. That doesn't change because you still have the same reactants, but it takes a lot longer for the gain in energy, gain in potential energy, okay. It hits the same peak as the original, but you'll notice that when it comes back down to start forming products, it won't start forming products until much later. So it forms products at a later time. Okay? So it forms products here, which is slower than the original, because the original formed the products right about here, okay, where this line is. So notice that the peak hasn't changed. You have the same activation energy. And the reason for that is inhibitors don't find alternate pathways, okay? They just prevent your reactants from reacting with each other, okay? So inhibitors do not make new intermediates. Okay. Well, some of them do, but the ones that we're concerned about, they don't make new intermediates. Therefore, no change in EACT. So why is it taking longer for this reaction to occur? Well, the answer lies in how inhibitors work. Okay, we'll just change our color back to black. Inhibitors are substances that delay a reaction by blocking or preventing reactants interacting with each other. Let's say from interacting with each other. Okay. Most of the time, inhibitors cause side reactions. These are just not useful reactions to the main reaction. It doesn't contribute to making products. They just do their own thing. Okay, so I'll give you a couple of examples here. There is a type of inhibitor called a competitive inhibitor. Okay, these guys compete for reactants. Okay, and by competing for reactants, they will cause side reactions. So example, there is a normal substance for the browning of vegetables and fruits. Okay, well, there's a normal reaction for that. Okay, so let's say browning of fruits. The normal reaction looks like this. There's a substance called monophenol. When it combines with an enzyme called tyrosinase, it causes fruit to go brown. Okay, so this is the enzyme, this is the substrate. The inhibitor is a substance called benzaldehyde. Benzaldehyde blocks tyrosinase from reacting. Okay. By binding onto monophenol in a side reaction. So if this is your monophenol, okay, and this is your regular enzyme, the inhibitor comes in and blocks out the enzyme. So the enzyme can't fit in that space, okay, and therefore slowing the reaction down. So the end result of this is benzaldehyde, prevents fruits from browning quickly. It just slows it down. Okay, so this is one example of an inhibitor. Inhibitors will cause side reactions, which doesn't change how the reaction works, it just slows it down entirely. Okay, so it just takes a little bit more time, so your graph basically shifts to the right. And that's all. That's all it takes.